Good day everyone, this is Villian V. Initan. In this video discussion, we will discuss about micrometer and how to read micrometer using English reading system. Objectives. At the end of the discussion, the students should be able to understand the history and evolution of micrometer, identify the parts of micrometer, measure the size of a variety of objects to within 0.001 inch accuracy, and determine micrometer using English reading. Before we start, we will have a short activity. Activity: Arrange Me. Instruction: arrange the jumbled letters from 7 jumbled words that will appear in each slide. In every slide, I will give you 5 seconds to think of your answers. First, what do you think is the jumbled letters? Very good. This is ratchet stop. Second, very good. This is thimble. Third, very good. This is frame. Fourth, very good. This is sleeve. Fifth, very good. This is locking knot. Sixth, very good. This is spindle. Very good. This is anvil. What is a micrometer? So what do you think is a micrometer? Okay. So micrometer is used as a piece of measuring instrument for making precise linear measurements. It is very useful to determine some tiny dimensions such as thickness, diameter, and lengths of solid bodies. The shape of this apparatus is like the English letter C. The frame of micrometer is fitted with a movable jaw, functioned by an integral screw. You can get the finest output from a micrometer. The calculation using a micrometer depends on the lead of the screw. Also, you can use the screw nut combination to put a better accuracy and depth in the measurement. M to M is one of the standard units of length measurement. Also, a mutual term is used for a micrometer. A micrometer, sometimes known as a micrometer screw gauge. It is a device incorporating a calibrated screw widely used for accurate measurements in mechanical engineering and machining, as well as most mechanical trades, along with other metrological instruments such as dial, vernier, and digital calipers. It is essential measurement tools used by mechanical engineers, machinists, and workers in other technical trades. They enable workers to take extremely fine measurement, which may be displayed in either imperial or metric formats. A micrometer is a measuring device used to measure flat surfaces or different geometries, for example, the inner diameter or thickness of a pipe. So now, let us proceed in the history of micrometer. The word micrometer is a neoclassical coinage from Greek mikros, meaning small, and metron, meaning measure. In 1670, English got it from French, and that its first known appearance in English writing. The people of that time did have much need for and interest in the ability to measure small things and small differences. So this is the timeline of the year of every micrometers that has been invented. During BC period, specifically in c. 200 BC or 200 before Christ era, screw thread is invented. So it was used by the Greek to raise water from a lower to a higher level. The idea of using these same threads for measurement did not exist then. It was during the 17th century when threads were utilized to measure the length of objects. Next, in 17th century, specifically in 1639, William Gascoigne invented a micrometer caliper comprising of jaws and scale. The system comprised of a rotating handle attached to the end of the threaded rod connected to a movable jaw. A reading was achieved by counting the revolutions of the handle against an attached disc. The disc divided one rotation into 10 equal parts. Thus, he could measure the distance covered by the moving jaw with accuracy. Next, during 18th century, specifically in 1772, James Watt invented the tabletop micrometer. So James Watt invented the first bench-type micrometer. A key concept of his design was magnification based on threads. In all history books, his name is always mentioned, and with a good reason. Without Watt, a history of micrometers cannot be written. His invention, briefly described, consists of a rack and pinion mechanism connected to rotating threads. James Watt was the first to employ a U-shaped frame and can be recognized as standard design for modern micrometers. Next, during the 19th century, specifically in 1805, Henry Maudslay invented the tabletop micrometer, or what we call Lord Chancellor. In the early part of the 19th century, Sir Henry Maudslay was known as the producer of best machine tools in London. His tabletop micrometer, called Lord Chancellor, was the most precise of that day and considered as the beginning of precision measuring instrument. Next, specifically in 1848, J. Palmer received a patent for his micrometer, or what we call Palmer system in France. As stated earlier, using screw threads for measuring linear distances has its own origin in Gascoigne's invention in 1638. Essentially, Palmer used the same principle in his compact handheld micrometer. However, his design was more advanced and marked the beginning of modern micrometers. Modern micrometers closely follow the Palmer system's basic design of a U-shaped frame, thimble, sleeve, spindle, anvil, and etc. During specifically in 1855, J. Whitworth invented a horizontal calibration machine and made it available for sale. It was Sir Joseph Whitworth who introduced one of the most remarkable instruments of that period, his millionth of an inch measuring machine, many of which were sold to the general public. Specifically, in 1868, Brown and Sharp invented pocket-sized micrometers for measuring plate thickness. In 1868, Brown and Sharp invented pocket-sized micrometers for measuring plate thickness. Brown and Sharp studied the micrometer they brought back from Paris and added two features: a mechanism to hold spindle threads better and spindle clamp. In 19th century, specifically in 1877, Victor Machine placed an ad for their micrometer in the inaugural issue of American Machinist. So the inaugural issue of American Machinist in November 1877 carried an advertisement placed by the Victor Machine Corporation announcing a new micrometer made in America. Next, we will proceed in 20th century, specifically in 1920 to 1935. Several Japanese manufacturers start producing micrometers. With the use of micrometers, they were able to measure products more accurately and quickly. Specifically, in 1938, Mitotoyo starts producing micrometers. To promote the first lot of micrometers, a special promotional towel was prepared, and it was a slogan: "Good, inexpensive, and long-lasting. The world's best micrometer." Next, we will proceed specifically in the year 1947. Mitotoyo restarts producing micrometer after World War II. Throughout the World War II period and even after, the production of micrometers encountered enormous difficulties. The nation awoke to a different world and slowly started to rebuild itself. Next, we will proceed in the year 1953. Mitotoyo produced the 3-meter outside micrometer, the largest in the world. So some of the improvements made were satin chrome finish thimble, sleeve, and frame, improved contrast of graduated lines and assured longer tool life. Friction thimble. In addition to the standard ratchet stop, this feature was added to provide constant pressure, making it easy for an operator to use it with one hand. Hardened and ground spindle threads to achieve higher accuracy and durability. Carbide tip measuring faces for more precision and durability. The conventional ring clamp was redesigned to a lever-type spindle clamp. Special purpose micrometers for threads and other forms were produced, and mechanical type digital counter was added to standard micrometers. Next, we will proceed in 1969. Mitotoyo started producing 3-pointed inside micrometer. Next, in 1979, first digital micrometer in Japan introduced by Mitotoyo. The introduction of the digital micrometer eliminated this possible reading error and became the preferred system for all users the world over. This advertisement introduced a new model called count micrometer. This feature was added to all models to make reading fast and accurate. However, the classic line graduated models were still produced because many seasoned machinists didn't need the digital counter. Next, we will proceed in the 21st century. In 2003, Mitotoyo introduced its first collant-proof micrometer, and in 2004, Mitotoyo introduced its improved ratchet thimble micrometer. The patented ratchet thimble mechanism helped ensure the repeatable results by transmitting micro vibrations along the spindle to the contact base to provide a constant measuring force and encourage good contact with the workpiece. Now, let us proceed in Micrometer Caliper. So this is the standard inch micrometer, accurate to 0.001 inch. The micrometer has wide application in all fields of science during different scientific experiments and in engineering to measure the values of finest objects up to higher precision and accuracy. So for better understanding and to ensure the appropriate use of micrometer, first, we must have to know its mechanism and basic parts, construction, and main function. So we discuss here the basic parts of micrometer and the main function of these parts in order to make proper use and avoid measurement errors. The typical micrometer, so that's normally, is called outside micrometer. So following are its parts: ratchet stop, thimble, frame, sleeve, lock nut, spindle, and anvil. Parts of micrometer. Ratchet stop. The micrometer ratchet stop can be found on the end of the handle, and it restricts the amount of pressure by enabling movement at a calibrated torque. It's a knurled thumb grip to rotate the spindle into desired direction for measuring process, provided with ratchet action to avoid over-tightening of micrometer across the measuring object and also ensure equal pressure force of each measurement. Next, thimble. You should gently apply pressure from the thumb in order to turn the micrometer thimble. This part features graduated markings which should be easy to read. Turns to open the micrometer, it also has 1,000th inch marks starting with 0 and going to 225 thousandths of an inch. Next, frame. Micrometer frames are C-shaped and ensure the optimum positioning of the anvil and barrel. Frames may take a variety of shapes and sizes, allowing for desirable functionality of the micrometer. The hub-shaped frame is ideal for taking highly accurate measurement in confined spaces. It holds the pieces together. Its C-shaped frame is a rigid part that has both holding points for a job or object to be measured. Its size depends on micrometer measuring range, so size of C-frame increases as range expands to bigger. Its main function is to provide basic structure of a micrometer, in which stationary anvil located at one end and movable spindle slides inward or outward through other end of C-frame. Next, let us proceed in sleeve or barrel. The round micrometer sleeve or barrel is kept securely in place and features the linear scale. It is also quite common for vernier markings to be found on this part of the micrometer. This scale allows highly accurate measurements to be taken in degrees of 0.001. A barrel type cylindrical part which mounted on spindle and is main scale of micrometer because main scale is engraved on the sleeve. Thimble rotates around that sleeve and spindle. Its main function is indication of the reading. Next, locking nut. The spindle micrometer locking nut is a particularly helpful feature when it comes to maintaining awareness of the measurement and securing the spindle for small lot gouging. Some micrometers come complete with lock nuts, while others have locking levers. Where possible, it is advisable to choose the locking lever variety due to the relative ease of use and maintenance. It works as stationary nut for this mechanism, so rotation of this mechanism into lock nut controls the spindle movement. Next, spindle. It is situated next to the measuring faces. The micrometer spindle is projected towards the anvil as direct result of contact with the thimble. It opens and closes as the thimble is turned. The space between the spindle and the anvil is the length that is being measured. Next, anvil. The micrometer anvil should be noticeably shiny. It should ensure that the spindle gravitates toward the object, which is firmly secured. The anvil will be kept in consistent contact with the part and may chip unless a high level of care is taken. Quality models typically come complete with carbide tip micrometer anvils, which allow for an extended tool life. It is a small piece that the spindle rests against when the micrometer is at 0.000, so we say it's one rigid measuring and holding print of micrometer. Principle of standard inch micrometer. The operator collects the data directly and precisely from the amount of rotation of an accurately made screw. The data is helpful up to a certain extent of the axial movement and vice versa via the constant. The name of the constant is known as the lead of the screw. The lead of the screw is a tool space that moves forward in an axial part. One complete turn of the screw can rotate 360 degrees. You can proceed with the data after you collect the right data, as it consists of the lead and major diameter of the screw. You can amplify the given amount of axial movement during the calculation. So there are two important terms in the principle of standard inch micrometer. So pitch is the distance from point on one thread to a corresponding point on the next thread. Inch threads pitch expressed as 1/n, or the number of threads, and metric threads expressed in millimeters. So pitch is the smallest division in main scale, and it is the precision of a micrometer is determined by the thread pitch of the spindle. The spindles of most imperial micrometers are threaded at 40 threads per inch. The thread pitch is therefore 1/40 of an inch, which is 0.025 thousandths of an inch. The distance from a point on the screw thread to a corresponding point on the next thread measured parallel to the axis. And lead, distance screw thread advances axially in one complete revolution. So lead is the inner trouble the nut makes per one screw revolution, and is how bolt screws are typically specified. In reading a micrometer, it takes practice. To learn to read the micrometer, you need to understand the thimble and the sleeve. Here, we are going to learn to read the micrometer by figuring out the markings on the thimble and the sleeve or barrel. The sleeve or barrel does not move. It looks like a ruler with 10 numbers. The space between each number is divided into quarters. As the thimble rotates around this sleeve, it covers up or reveals the numbers marked on the sleeve. We must know that the zero line on thimble lined up with the index line sleeve or barrel. Its measuring faces just touch. Pitch is 1/40 with measurement of 0.025 thousandths of an inch. Since 40 threads, one complete revolution of spindle, one line appears. Every fourth line longer represents 0.100 inch. Thimble has 25 equal divisions. It represents 0.001 inch. Now, I will play a video for you to fully understand the micrometer and how to read a micrometer.
Okay, this is how to read a inch micrometer. Before we start talking about how to read a micrometer, especially an inch micrometer, we want to think in thousandths of an inch. So this is 3 decimal places. If we just always set our thought process to 3 decimal places, we'll see that a micrometer will work pretty easily. This is the way that machinists think. So you're going to think of 0.001 as 1 or 1,000th. 0.020 is 20 thousandths. 0.9 would be 900 thousandths. A quarter of an inch, you would say, is 250. 0.375, think of that as 735. So how much is a thousandth of an inch anyway? Kind of some rules of thumb. If you're thinking of a piece of paper, that's about 4 of these. 0.004 or 4 thousandths. A quarter is about 70 thousandths, or 0.070. A pencil, a normal wooden pencil, is about a quarter of an inch. Think of that as 250 thousandths. 0.25 is a quarter of an inch. Okay, so there are two scales to look at on a micrometer, the barrel scale and the thimble scale. We'll look at the barrel scale first. So here's the barrel scale up close. You'll notice that it's got some numbers across here and some tick marks. Now, if an inch micrometer is reading from, say, 0 to 1 inch, then this scale is, well, they're tenths of an inch, but this would be a half an inch, so that's 0.5 or 0.500. This first main graduation here, the first big division from 0 to 1, this is 0.1, so that's a tenth of an inch, or if we're thinking in thousandths of an inch, that's 100. The next big mark is 200, or 0.2, so 0.200. We'll say that is 200, and that will make it easy to keep the decimal place straight. Down here, that's a half an inch, 0.5. Now, if this first mark is 0.1, or 100, half of that would be 50, or 0.050. So the halfway between 0 and 0.1 is 50, or 50 thousandths. Half of that distance would be a quarter. So if you're thinking in terms of thousandths, this would be 100, 25, 50, and then this mark would obviously be 75, 0.075. The main scale, if we want to read these together, is 0.1. Somewhere out here, this would be 0.4, or 425, 0.425. Down here, can you guess what this would be? This would be 0.675, or 675 thousandths. Now, the other scale is the thimble scale, and you'll see that it starts at 0 and goes from 1, 2, 3, 4 all the way around to 20, 21, 22, 23, 24, and this would be the 25th. So these are thousandths of an inch. So if this says 1, this is 1,000th, 0.001. 5 would be 0.005. 17 is 17 thousandths, 0.017. Now let's look at a reading on here. This mark that you see there, that tells us that we're at 0.3, and then 0.325, 0.350, and 0.375. So that mark represents 0.375. The reading from the thimble scale is 0, so we don't add anything to the 0.375, and so the reading is 0.375. Okay, so here I've taken the micrometer and I have moved it just a little bit back, so we're just a little bit less than 0.375, and the question is, what's the reading now? Well, we're not reading from this mark anymore. This mark is not actually showing, even though you can kind of see it. The fact is that if this mark were to show, it would be a brand new mark, and so the reading on the thimble scale would be a very small reading, and as you can see, we're reading 24, which is almost completely all the way around. So this is a very high number, so that means we're working off of the older mark, which would be this one. And that mark would read 0.350. Now, we can get the next decimal place by reading the thimble scale, and this one, remember, is reading in thousandths of an inch. So this is 20 thousandths, 21, 22, 23. This is 24 thousandths, so that's 0.024. So the reading of this micrometer is the 0.350 plus the 0.024. Think of it as adding 350 and 24. You get a reading of 0.374. Now, on this slide, we can see that we've gone past the 0 mark. So we're working off of a brand new number. It's a brand new mark. It's going to be a small number since it's brand new. We've moved from 0.3, 0.325, 0.350, 0.375, and to that we're going to add 0.001. So if I asked you what is 375 plus 1, you'd be able to tell me it's 376. So that's the reading.
So, from the video that I play, you already know how to read a micrometer. Am I right? Okay, so standard inch micrometer reading. So let me give more examples for you to fully understand how to read a micrometer. So you must note that the last number showing on sleeve and multiply by 100,000ths of an inch. So first, you will identify on the sleeve the number 2. So let's multiply it by 100,000ths of an inch. So that is equal to 200,000ths of an inch. Very good. Next, we must note the number of small lines visible to the right and multiply by 25,000 of an inch. So there are 3 lines that have been seen in the picture. So 3 times 0.025 is equal to 0.075 or 75,000ths of an inch. Very good. Third, note that number of divisions on thimble from 0 to line that coincides with index line on sleeve and multiply by 0.001 or 1,000. So the number on the thimble is 13. So let's multiply it by 0.001. The answer would be 0.013 or 13,000 of an inch. Very good. So now we will add 3 products to get total reading. So first, we see in the sleeve the 0.200. Next, 0.075. Next, 0.013. So the total of micrometer reading is equal to 0.288 inches, or what we call 288,000ths of an inch. Very good. Okay, let's have more examples. So first, we will identify what number that we seen in the barrel scale. So first, we see number 2. So that measures 200,000ths of an inch. Next, we see only one line. So that measures 0.025 or 25,000ths of an inch. Next, in the thimble scale, we found out that there are 3 lines that straight throughout the barrel scale. So that measures 3,000ths of an inch or 0.003 inch. So let's add them. So the total of the reading is 0.228 inch, or what we call 228,000ths of an inch. So this is another example of how to measure standard inch micrometer reading. So first, okay, so now to read standard inch micrometer, you must note that the last number showing on sleeve and multiply by 0.100 or 100,000ths of an inch. Note number of small lines visible to right and multiply by 0.025 or 25,000ths of an inch. Third, note number divisions of thimble from zero line that coincides with index line on sleeve and multiply by 0.001 or 1,000th. Then you will add three products to get total reading. Next, we will proceed in how to read Vernier micrometer. So Vernier micrometer, it has the scale consists of 10 divisions that run parallel to index line. Vernier scale is added to the sleeve, and it has also the friction thimble, and each division on Vernier scale has a value of 0.001 inch. Okay, so to read Vernier micrometer, read as with a standard micrometer. Note line on Vernier scale that coincide with one on thimble indicates number of 10,000ths. Multiple the line number times 0.0001 and add to total of the readings. Now, let's watch the video about how to read Vernier micrometer and add to total of the readings.
In this video, we'll discuss how to read a Vernier micrometer. Once you've measured your workpiece and locked the spindle using the spindle clamp, you can read the micrometer to determine the value of the measurement. Micrometers may have 2 or 3 sets of graduations depending on whether or not your micrometer has a Vernier scale. The first set of graduations are on the sleeve, perpendicular to the spindle, and on inch micrometers like this one, they're typically etched at 0.025 inches or 25,000ths of an inch. The second set of graduations are etched on the thimble. These are typically etched at 0.001 inch or 1,000th intervals. The third and last set of graduations, which are not present on all micrometers, is the Vernier scale. These are located on the sleeve, adjacent to the first set of graduations. The Vernier scale is used to read 0.0001 inch intervals, also called 1/10,000th or more commonly called 1/10th intervals. To read the first set of graduations, note the last line which is fully visible. The main set of graduations, by fully visible we mean not covered by the thimble. This can be difficult to do by visually comparing the thimble and sleeve directly, so if you are unsure of whether or not the thimble is covering a line, remember that the numbers on the thimble increase as the micrometer moves out. So if you have a high number, then it has not yet passed the graduation. If you read a low number, then it has just passed the graduation. In this micrometer that we have locked a reading into, the last line, which is fully visible, is the 5th hash mark on the main scale. So the reading for that would be 5 times the graduation of the main scale, which is 0.025 inches, for a reading of 0.125 inches. The second set of graduations is read by finding the line which is nearest but not past the line running down the sleeve. An easy way to make this determination is, if the horizontal line is between two thimble graduations, use the smaller number. In this case, the line is between 13 and 14, so we'll use 13. And on this micrometer, that's 0.013 inches or 13ths. To read the Vernier scale, we look at all of the lines in the scale and note how they line up with the graduations on the thimble. Only one of the lines on the Vernier scale will line up perfectly with the graduations on the thimble, and this is our reading. In this case, we can see that the 5 is the only graduation which is perfectly in line. The 6 is a little bit inside over here. The 4 is a little bit inside over here. So the 5 is the correct reading. In this case, that is 0.0005 inches or 5/10. The final reading is the sum of these numbers. So 0.125 inches, 0.013 inches, and 0.0005 inches for a final reading of 0.1385 inches.
Okay, so now you already know how to read Vernier micrometer. Am I right? Okay, so first we will identify the number in the sleeve. So we found out that there's number 2. So number 2, that measures, very good, it measures 0.200 inch or 200,000ths of an inch. And next we see 3 lines in the sleeve. So that measures 0.075 or 75,000ths of an inch. Next, we will focus on thimble scale. So we found out that line is number 11. So that measures 0.011 or 11,000. Next, we will move on the Vernier scale. So the line straight within the thimble is number 2. So that measures 0.002 inch. Very good. Now let us proceed in example number 2 of the Vernier micrometer reading. So first, we will focus on the sleeve scale. So the number that we found is number 2. So that measures 0.200 or 200,000ths of an inch. Next, we will found the first line of after the 2. So the number is 0.025 or 25,000ths of an inch. Next, we will focus in the thimble scale. So it has measurement of 22. So that means it measures 0.022 or 22,000ths of an inch. Next, we will focus in the Vernier scale. So what is the number coincides straight line in the thimble scale? Did you find it out? Okay, very good. 0 is the straight line coincide between the Vernier scale and thimble scale. So we will add all the measurements. So first, we will add 200,000ths, 25,000ths, 22,000ths, and 0.0000 inch. So it measures 0.2470 inch. Now, let me present to you the applications of micrometer.
Everybody, welcome back to the shop, and today I'm going to be making a very simple how-to video on how to read a micrometer, and this will be for imperial measurements. So this is a 0 to 1 mic that I'm going to be using for demonstration. So I've had a lot of requests for making very simple basic videos like this to try to help people along. We have a lot of viewers that are in school or new at machining and metalworking, and they look to these YouTube videos to try to help them along the way and learn how to use these tools. So I want to show you how to read a micrometer, and I have several other types of how-to videos I'd like to make as well pertaining to measuring tools and things like that. All right, so we're going to use my my good trusty 0 to 1 Starrett micrometer. This was also my granddad's and my dad's, so you're looking at a third generation mic there that's been well used for many years, well over 40-50 years probably. All right, so I want to point out also that this is a ratcheting micrometer, so you have a ratcheting thimble there on the end of the mic. There are several mics that you can buy that do not have the ratchet thimble on the end. The purpose of the ratchet is so that whenever you go to take your measurement, you use this and it applies the proper amount of torque to the mic, giving you the proper reading. So if you're using a mic without the ratchet there, you have to be careful on how much pressure that you apply to the screw here whenever you're getting your feel. Okay, a lot of times whenever I'm using a mic, even if it has a ratcheting thimble, whenever I'm holding it, I'll use the side of my finger to kind of pull it very gently to get the proper feel on the measurement. And you'll kind of, once you get some practice, you'll know what the proper feel is to use your finger to move the barrel there. All right, so I will show you this. We've got this standard right here. So this is a Brown and Sharp. This was my granddad's here, and we'll use this to check the mic that we're using there and make sure that we're on. This is another good thing to show you for the guys that are learning this stuff. So I'm going to put this in there, and I'm holding this mic in a clamp here to try to help with the video. So this isn't normally how I measure things, but just trying to bring you some good video there. So we're going to put the gauge in between the anvils there and get it centered up, and I'm just using a ratchet thimble, and I can feel it that it's in there properly. And we zoom in there, I think we can see that our 0 point right there is near perfectly lined up with this horizontal line going across there. So that's your reference line on your micrometer in the center there that you're going to be referencing this barrel to right there. So we have a good mic. We're right on size. So we'll go ahead and take that out of there, and we'll go ahead and begin with what all these numbers and lines mean on a micrometer. So to kind of start with, the way that I always like to look at it when I was trying to learn this stuff too is no matter what size mic you're using, you have a 0 to 0 measurement there. That's 0 to 999 thousandths. So this is the distance of 1 inch right there. And if you imagine these 2 points of reference, this 0 and 0 there, you have 1,000 equal places in between there, and that's where you're getting your measurements. So you'll notice you'll have a 1 on the top here. You have a 1, 2, 3, and so forth. So that's 100ths. So that's 100 thousandths, 200, 300, all the way up until you get to the full inch there. All right. Also on the top line, let me see if we can get you in a little bit closer. No, that's it. You also have a line in the middle there, so that's 50. So that'd be 50 thousandths, 100, 150, 200, and so forth. There's 250, 3. Alrighty. On the bottom of that line, I know it's a little bit harder to see there, but each one of those lines is going to represent 25 thousandths of an inch. So starting with your 0, first line will be 25 thousandths, the second line will be 50, third line will be 75, and then the fourth is going to be exactly 100 thousandths. All right. So let's go ahead and we'll run the barrel in just a little bit here. We'll bring it on in so that's a little bit easier to see what's going on. So let's go to, we're going to go to 100. I'm going to line it up on a 0. But what I want you to know now is all of these numbers on a barrel. You see we start with 0 and it counts, 1. And as we go all the way around, you're going to end up, there's 24 and then there's 25. So each revolution of the barrel is 25 thousandths of an inch. On the bottom there of the barrel, you'll see each line is 25 thousandths. So each time you go around, so right there we're at 125 thousandths of an inch, 126, 127. So you add up the top line and the bottom line, and then whatever division that you're on the barrel here, lined up with the center horizontal line, that you add that together for your total measurement. So if we was to be measuring that right there, all right, so that would be 134 thousandths right there. All right, I've got a couple of gauge pins right here. Actually, we have a standard that we'll use. This is another Brown and Sharp. This is a 2-inch standard, and we'll measure the diameter of this pin right here. So we'll stick it in there, and we'll go ahead and use our ratchet, and then make sure we're squared up nicely. So let's see what we ended up on. So start with 2, because you know you've already passed the 2. All right, you can look at the top line and see that we're at the 50, but if you count the bottom, you know that you have 2 lines that you've passed, so 25 and 50. So you have 200 plus 50 plus 9, because you see the line, the 9 is lined up with that line right there. So we are at 259 thousandths measuring the diameter of this pin right here. All right, we got a couple more that we'll use for references, and I picked these out because these are kind of standard sizes. So 375 thousandths is the diameter of this gauge pin right here. That's also the same as 3/8 of an inch. So we know we've hit 3, so that'd be 300 thousandths. And then you've got 3 of the 25 thousandths divisions, 25, 50, and then we ended up on our 0 for our last revolution there, so that's another 25, so that's 375 thousandths of an inch. Now, you also have tenths on this micrometer right here, which I can't really show you. I'm going to have to reconfigure the tenths there. So on the tenths, if you're past the 0, so it actually looks like we're past that 0, I'm going to say 1 to 2 tenths past that. You have to go up on the top of the mic to line up one of these numbers on the barrel to indicate how many tenths past you are, and we'll look at that as well. All right, so here's one more gauge pin that we'll measure for reference there. This is a 437 thousandths gauge pin. And you see it's got the plus on there, so it is going to measure just slightly over 437. That's going to be in your tenths range. All right, so this would be 7/16 standard inch sizing right there. All right, let's zoom in there and check out what it reads. So again, you already passed the 4, so go ahead and say 4.4. You already passed the 25 thousandths division there on the bottom. All right, and then you've gone around and you're lined up on the 12. So the way I read that is 425 plus the 12 thousandths. That's going to equal 437 thousandths once you add all those up. All right, I'm going to demonstrate the tenth reading on the top of the mic now. We'll go ahead and put our 437 back in here and clamp it back in. So we already know we have a 437 thousandths reading, but our 0 is just slightly past. But if you'll notice on the top of the mic right there, on the top of that barrel, all right, there we go. You see you have a series of parallel lines starting with 0, 1, 2, 3, 4, and it goes all the way around to 9. And if you'll look over here, this number 16 is perfectly in line with that number 1 line right there. So this is 1/10. The one after that would be 2/10, and you can see it's slightly off. Okay, so I'm going to call it 16 as being the one that's lined up with the number 1. So we are at 0.4371, the 1 being the 1/10. So that's how you split 1/1000ths of an inch, is lining up whichever one of these lines, 0, 1 through 9, is perfectly in line with one of these numbers on the rotating barrel. That's what you add to your figure that you come up with. One more quick note that I want to point out about a 0 to 1 inch mic is that that's the only OD mic that you can run the barrel all the way in and touch both anvils just like that. And it's important to note that you should never leave them together like that, especially whenever you're storing them. So if you're going to put this mic up, don't run it all the way in there until it's tight and leave it like that. One trick that you can do is put a little piece of volatile paper in between there and run it up. That way it keeps the anvils oiled and not jammed in there together. So always just leave them apart just a little ways. It doesn't matter how far. Just run them out a little bit whenever you go to put it back in your case or put it in your toolbox. All right, guys. Well, I think that's going to conclude this how-to video on how to read an inch micrometer. And hopefully you guys liked it, and I'm hoping that it helped a few of you guys out there that's trying to get out there in the shop and learn how to do the machining and the metalworking and the precision measuring and things like that. So if you have any other suggestions for some tools that you would like to see me demonstrate here on a how-to, be sure to leave me a comment, and hopefully you leave me a thumbs up and you enjoyed the video. So until then, we'll see you on the next one.
So I have prepared here an activity for you to practice to check your understanding about the micrometer or how to measure the micrometer. Exercise 1, you will determine the measurements of the following and show your solutions. That's 1 to 8. And then exercise 2, you will identify the parts of micrometer. Okay? These are the sources of my presentation, and that's the end of my presentation. I hope you've learned something. Thank you for watching.